Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, January daily challenge. Subarray sum divisible by k. So we get basically an array, and we get an integer k, and we want to return the number of non-empty subarrays that have a sum that is divisible by k. And subarray is, of course, just a contiguous portion of the array. So if we take a look at this example with k equal to 5, the entire array itself is the sum of it is divisible by k, because we have 5 here and then we have 10 here, so it's 15. 15 is divisible by 5. Here 5 alone with just this subarray is divisible by 5, and then also this entire one with 5 and 0 is divisible by 5 because the sum is 5. Also here is divisible by 5 because the sum is 5 minus 5, right? So overall 0, and 0 is divisible by 5, right? And same thing, this one is minus 5, which is divisible by 5. This one is minus 5, also divisible by 5, right? So that's the idea, and the goal is just to return the total count, okay? And you can see here the length of the array can be 10 to the power of 4. So this tells us that basically an oven squared algorithm would not work, because then it would be 10 to the power of 4 by 10 to the power of 4, and that will always get time limit exceeded on Leetcode. But if it wasn't if it was possible to do it in oven squared, then we can just try every possible subarray, right? But that's not possible with this constraint here. So let's see how we can solve it. So first, to solve this problem, I think one concept that is good to understand is prefix sum. And actually this comes up a lot when you have any problems that have the notion of finding the number of subarrays that equal some sum or divisible by sum or whatever, anything related to counting subarrays that have certain sum property, right? Often the prefix sum helps, right? But first I want to explain how it helps, and first I want to explain the concept of prefix sum itself. So I have an array here, right? This is my array, and I have the prefix sums computed here. The prefix sum is just basically for each element you take the previous prefix sum from the previous index and you add the element. So here before we had 0, so the prefix sum is just 3. For 5, the previous prefix sum 3 plus 5, that's 8, and this represents basically just the sum of this subarray, right? And then we add 1, and so 9, and so this value here represents the this value here represents the prefix sum for this subarray, right? And then again 6, we add 6 to 9, that's 15, and this represents the prefix sum for this subarray, and you get the idea all the way till the end. But the nice property about prefix sum is that you can easily find the prefix sum of a range in the array itself that is not from the start. So that what that means basically is that, let's say we want the prefix sum of this subarray here from 162. Let's say we want the sum of just that subarray. We can do it in O of 1 operation. Let's say if it was a long one, we can do it in a way where we don't need to count the sum of calculating each element, adding it together. How? Because what you can do is just take this prefix sum here at the end of your subarray and the prefix sum just before your range, which in our case here is this one. So the prefix sum just before the first element and at the last element, and you could just take the difference. In this case, it's 17 minus 8, right? And so that's 9. And actually, if we do this, 1 plus 6 plus 2 is 9, right? And so that's where prefix sum is useful. Then there is another additional thing where it's even more powerful, and that's if you combine that with a map. So let's say you want the prefix sum that is equal to some k value, okay? So you want subarray that has a sum equal to k. Yeah, so this concept becomes even more powerful if we combine it with a map. Let's say, for example, modify our problem a little bit, and let's say we were looking for the sum, subarray of sum equal to k instead of divisible by k. Okay, so how do we represent a subarray in our case here? In a general one that can both encapsulate an inner subarray and an array starting from the end. Well, what we said is let's just have it with the last one minus the one before. And for these that are starting from here, we can just consider that before is equal to 0 because before doesn't add anything to the sum, right? And so let's call this index j, and the starting position just before the starting position, let's call that index I. Okay, so what is the sum of this portion here? It's just s of j, the sum of the prefix sum ending at j minus the prefix sum ending at I, right? And so what we are looking for is a subarray that has this sum, right, equal to k. That's what we are looking for, okay? So for a prefix sum, let's call prefix sum just p of j, and prefix sum ending at I is equal to I. For this to be equal to k, what do we need? So this basically means that p of j minus k, right? If we do put k to the other side and put I to the other side here and put k here, this would mean p of j minus k equal to p of I, right? Okay. Is equal to p of I. So what does this tell us? Right? P, by definition here, p of I is before p of j, right? So what does this tell us? This tells us basically that if we are at position j, right, and we want to know if we had a subarray that has a sum equal to k, all we need to check is if there was a value that we've seen before that is equal to this, because that would mean we've seen a pi value, which would mean with this formula here, we have a subarray sum that is equal to k, right? So that's the clever part. And so basically what this would mean is that if there was a sum, a prefix sum before j that is equal to p of j minus k, then that means subarray I plus 1 to j has sum equal to k, right? Just by using the formula that we did here, right? And this is easy to check for. We can just, as we do the prefix sum, we can just keep track of of all the sums we've seen so far, and that way, let's say even if we had multiple, let's say we had, let's say maybe we had some sum like this, and we had another sum like this. So let's say I was here and was here. And for both, we would have for both the same sum. This is just taking an example. Actually, let me just do an example that works. Let's say we have two subarrays, like 1, 1, and then 0, 1, 1, right? And then some prefix sum here, right? Then what we need is we do want to count both this one and this one. So we need to actually, we have as many subarrays that have sum equal to k as the count of this value that we can find. Okay, and so that's why we need a map of the sum and the count that we've seen so far, and then we would know how many subarrays equal to k that we have, right? Okay, so now let's run it on this example, so a little bit, and from there we can apply this to the modulo k. So let's have a map here, And so first we have the sum 3, we have only 1. And then we have sum 8, we have only 1. And so how do we check? Now we check just the prefix sum, which is we just check if we've seen 8 minus, let's say our k is equal to 7. We just check if we've seen 8 minus 7, which is equal to 1. We haven't seen it, so we proceed. We don't have a subarray of sum 7 yet. And so we add 8, and then we add 9. Have we seen 9 minus 7, which is 2, 8, 9, right? We haven't, and so we don't have a subarray of sum 7 yet. So we add 15. Have we seen a subarray that is, so 15 is 1. Have we seen a subarray of 15 minus 7? So that's 3 plus 5, 8. Yes, we do. We do have it here. Right? So that means, or in how many counts? Just 1. So that means we have a subarray of sum 7, because, and what is that subarray? That subarray ends at this position, right? And it starts just after the one at 8. So it starts just after this one. And so that's actually 6 plus 7, right? This is the subarray of sum 7. And that's exactly what our solution told us, right? And so you can see it works for sum equal to k. Now the challenge becomes, how do we apply it to the modulo case? Let's take a look then. So the modulo case is actually pretty similar. So we know that we need to calculate the prefix sum. We will need to do the same thing with the prefix map. The only thing we need to change is, how do we apply this formula? Because it's not the same thing. It's not that it's equal to k. What the problem says for us in this case is divisible by k, right? So basically what it tells us is that p of j minus p of I needs to be, modulo k needs to be equal to 0. That's exactly what divisible by k is. So the subarray sum needs to be, which is equal to this, so this is the subarray sum, needs to be divisible by k, and divisible by k means modulo k it's equal to 0. And so what this would mean is, let's apply our modulo. And so this means that pj, let's just enter it, modulo k minus p of I modulo k, so just mathematically, needs to be equal to 0. Okay, so this is what this formula tells us. Now this is here, let's just give this a name. This is the remainder of the division by k. And so let's call it r of j, and let's call this r of I. So what we have here is that they are equal. So what this would mean is that basically exactly the same thing we did here, where we were, except we were searching for pg minus k. What we need here is actually, for each j, let's look for the same, if we've seen the same reminder before, because if we've seen the same reminder, that means there is an I position that has this valid, because we just did a formula and we got mathematically that this is equal to this. And so if we find that we've seen an index I before that is smaller than j, right, such that it's the same reminder, that means we do have a subarray that has this formula, right? Because this formula, the last one, is a direct result of this one, of the first one. Okay, and so if we find an I that we've seen already from our map, then that means we have subarray. So this is the same logic we applied here for the sum equal to k. And again, for the same reasons I mentioned here for the sum equal to k, where we need to, if we've seen it twice or 3 times or 4 times, we need to count that many of them, right? Because that means it's different subarrays. Like here it's this subarray, the other one is this subarray. And so for each I, basically what this would mean is that for each prefix sum in our prefix map, what we will need to change is for each prefix sum, for each index, we will save the reminder, and we will add that we've seen it. And so if we've seen it multiple times, we would have a count of 3 or 4. And so for next j, if we find a reminder that is equal, we will count that we've seen a subarray that has a sum that is divisible by k. Yeah, so that's pretty much the idea here. I hope that was clear. Just start from the idea of the prefix sum, and that idea allowing you to find quickly the sum of a range, and then from there that idea allowing you to see by looking at if you've seen some sum before, it tells you if there is some property for that range, and from there we could just do this formula and calculate our case with subarray sum divisible by k. Yeah, so that's pretty much it. That's pretty much the idea. Now let's implement it and make sure it passes our test cases. Okay, so let's do the implementation here. So what we need first is the length of the array. And we need to have a prefix map for our that we've mentioned that will store the values for us. And there is only one caveat, is that what if the subarray sum that we are looking for is actually starting from the initial position, right? What if, let's say, maybe k is equal to 5, and we have this, and then we have something like this, an array like this, right? So in this case, this is actually a valid prefix sum, and this also is valid prefix sum that is divisible by k. But the problem is we only will measure if we find a previous index where the remainder of that is equal to the remainder of I. The remainder of the sum, the prefix sum, is equal to the remainder of the prefix sum at j is equal to the remainder of the prefix sum at I. But since there was no prefix sum before, we won't find a solution. And so how do we fix that? Well, let's just mark that 0, which is actually almost as if we had a prefix sum before equal to 0. And that's sort of right, because when you have an empty, the sum of empty is 0, right? And so let's just mark that we've seen a counter in our prefix map. We've seen a counter of 0 equal to 1, so that we can, these cases that start from 0 can work. Okay, so that's the only thing to remember here. And this also, by the way, applies to all the cases, all the similar problems where we are doing a prefix sum, and you are doing a count for how many sums you've seen so far, right? And so here we will go through the array for each index. We just need to keep track of the current sum and keep track of how many subarray sums that are divisible by k. And so for the current sum, we just need to add the number at I. And now what is r of j? At I, right? So maybe let's call this j just so that it's similar to how we were thinking. So rj is actually just current modulo k, right? And what is ri that we are looking for? Ri should be the same thing. So we are looking for some value that is equal, that we've seen before, that is equal, that has the same remainder. This is actually what I'm... So if this exists, that means there is an ri. So that means there is a prefix sum at position I that tells us that the sum between I and j, the subarray sum between I plus 1 and j is divisible by k, right? That's what we've seen in the formula. And so that means we need to count just how many we have. So if we have multiple at different I positions, then we want to count as many of them, because each of them means a different subarray has a sum that is divisible by k, right? And so that's exactly what we have here. And we need to say that we've seen this value once at this position j, so that for future j we can use this, right? And then at the end we want to return count. Now, just one slight modification I want to make here is that so that this current value doesn't grow, we don't need it to grow. We just need to know modulo k what's the value. So instead of doing this, we can just say current modulo equal to k and actually use that current here. okay? And sorry, this is J because we changed the index. And this is current because we changed RJ to current, right? And so that should be it. Now let's just run this and make sure it passes. Looks good. Let's submit. And that passes test cases, right? Now, now in terms of time complexity, what is the time complexity for this? I hope this solution was clear. Just run it on more examples and you will see. So it's O of n time. In terms of space, we are using this extra map. So it's also O of n, is it O of n space or O of k? That's a good question, right? And in reality here, let's see how many, what are the values possible for this current here? We can only have modulo k, right? We can only have current is always, we always do modulo k. That means current is always smaller than k. Okay, that means the number of entries in prefix maps are always smaller or equal to k. That means actually the space is O of k space, right? So that's why also you can use an array here of k entries. So that's the idea here. I hope this makes sense. Please like and subscribe and see you on the next one. Bye.